introduction, and thank you for being still here despite the hour. I will try to give you in this hour, or better about 50 minutes, a flavor of more the theoretical part and background on what should be a pipeline for the chemometric analysis of experimental data, of course, especially within the framework of aquaphotomics. So I will try to cover, you've seen many nice tutorial in this first three parts of the workshop, and I will try to go more into the details of what the different techniques are and what they can offer for who is interested in the aquaphotomics application. And of course, I will try to be very fast in things that have been covered, and very fast about some particular parts of the presentation. This was aimed as a tutorial talk, so some slides would be very basic, some other will go more in depth into the theory. So I will try to go at different velocities depending on the task and on the topic. So of course, chemometric tools, that means like the statistical and mathematical approaches that are applied to the experimental data, in this case the spectroscopic data, for extracting relevant information, are like a relevant part of the toolbox that can be used for processing the experimental data within the context of aquaphotomics. And of course, we have many ways of representing the experimental data. The way that we are mostly familiar with is in the form of a spectrum, of course, and of many spectra when we are dealing with different samples. But for all the mathematical and chemometric methods that we wish to use, a more comfortable way of representing the data would be in the form of matrices. And in such matrices, of course, we will have as many rows as the number of samples that we are investigating, and as many columns as the number of variables that we are measuring on the different samples. And you may see in this very schematic representation the equivalence between analyzing a set of samples and putting the experimental results of this data into a matrix. And also, given the matrix of experimental data that we have, we have a more spectroscopically oriented way of representing it. That would just mean take the data in the matrix and do the same spectra or do the same graphical representation that you see there. So it would be just taking the opposite transformation and or representation than we've seen in this slide. But sometimes what we are mostly interested in is a different way of representation that we normally would call a row space representation, where each row of the experimental data matrix, so each profile that is used to describe our samples as thought, has been part of a multidimensional space and describing a point in this multidimensional space. Ideally, we would like to use and stress this representation because this is the representation that gives us information about differences between samples. So we want to characterize what makes one sample different from another. So it's the equivalent geometric representation of using and collecting data within an experimental matrix. And of course, when we have hundreds or thousands of variables describing our data, using directly the spectroscopic data for such representation becomes unfeasible. And we need models. We need models to encode the information that is present into the data. In general, not only for the representational part, and we will describe much of these models, information in chemometrics is encoding in a way, in an approximate way, into the forms of model. And the advantage is that in general, not always, but in general, when we are dealing with spectroscopic data, models that we are favoring is so-called bilinear models. Bilinear models are models that help us to summarize the main sources of variation within the data into a set of, let's say, profiles that we associate to some phenomena that are responsible of the observed variability or variance within the data, and relatives amount or scores that we use for describing how much of that variation is present into the different samples that we are measuring. Based on this very general and very tranchant description of the backgrounds of chemometric analysis, then in general, and of course aquaphotomics application do not make any exception in this framework, in general, when we think about a set of experiments and a pipeline for using chemometrics and for designing and processing the results of this experiment, then we would start with a sort of design of experimental design that should guarantee that what we are measuring is consistent with the objectives of our study. Then we do the measurement themselves, of course. Then we need to transform data in order to meet the requirements of the successive analysis that we want to do. And more, let's say, more precisely, we need anyway to try to use sort of a magnifying lens that puts the focus on the sources of variation that we're interested in the data, and try to move as far as possible for all sorts of detrimental or interferent or not interesting information that we may, or variance, sources of variation that we may incur with once we are considering our experimental data. And that, of course, okay, also in this case, division that I made is, I would say, a little artificial, but we can think of a general framework, of a general exploration of the data that we would normally do by means of bilinear data such as principal component analysis, even if that particular technique, although probably used or usable in more than 90% of the occasions, is not the only one for completing the task. And then further possibilities, and I wouldn't say these are the only one, but further additional possibilities could be those of trying to do resolution of the data, meaning that we want to start from the experimental data and extract profiles that summarize the variability in the data that are chemically or spectroscopically relevant, or some sort of supervised modeling that may be for qualitative, and in this case we would speak of classification, or quantitative variables, and in this case we would move into the realm of multivariate calibration or regression. A fundamental part of all this discourse is that, of course, we cannot be satisfied with any possible models until or if we don't do any proper validation of the results. Validation that is sometimes thought of covering only, let's say, the predictive part of the models when predictions are involved. But validation is a general concept that involves validation of the underlying hypothesis that underlie the models that we're using, of the stabilities of the extracting profiles, such as the loadings, even when they are unsupervised, or in general, of the consideration of all the consideration, of course included predictive ability, but not only limited to predictive ability that we do once we are doing our models. And I will try to briefly cover some of these aspects, also considering the time constraint that we have within this workshop. Of course, spectral pretreatment. We have already listened to a very thorough first workshop about the ways of removing or controlling for spectral variability. And so here I actually just left some couple of slides that I had about some methods that we are normally use, especially within the framework of infrared spectroscopy, to try to remove specific sources of variation. Of course, the attention is mostly, or for the sake of simplicity, is mostly focused on additive and multiplicative effect, because those are the ones that one is, let's say, more likely to find, especially in the near-infrared spectroscopic range or the mid-infrared spectroscopic range, because they are due, or they at least may be partly due to scattering phenomena, but not only to them. And of course, one could use, let's say, the same sort of linear correction, be it by standard normal variate, that has the advantage of not requiring any reference spectra for the correction, or with the standard, with the analog multiplicative scatter correction, where we need, especially in order to have a feasible solution to the linear regression problem that is underlying the method, to choose for a suitable reference spectra with respect to which to synchronize, let's say, or to align all the other spectrum in the data set. And this is just a graphical. Sorry? This is just a graphical illustration of how, for one particular sample, multiplicative scatter correction could be given the reference spectrum. It was already mentioned, and one particular pretreatment that could be useful, especially in this case in the context of aquaphotomics in particular, is the extended version of the MSC pretreatment. This is because, of course, this allows to express the spectral variability that one observes in one particular spectroscopic signal as the contribution not only of hypothesized linear and additive, so multiplicative and additive effect, but also one can take into account the possibilities of modeling baseline according to whatever form, in this case, using a quadratic polynomial assumption, and also one can decide to declutter the spectra from the contribution of possible interference, provided one could have a suitable spectral profile to consider as representatives of the interference that one would like to declutter the signals from. Also in this case, once we had a reference spectrum, possible interference spectrum, or a shape of baseline that we want to assumption about the shape of the baseline that we want to remove, then estimation of parameters can easily be carried out by means of multiple linear regression. And as an example of this, it was cited in a question in the beginning of the workshop. I would use an example that was taken by a paper by that we did in cooperation with Rumian and Nifagoen about measuring salt solution in water. And here you see that data, when you consider as a description of the data per different salt data set, the first principal component, then if one looks at the loading when only a standard normal variate was used as spectral pre-processing, they are quite similar to the loadings that one would obtain directly by analyzing or taking the first principal component of a series of spectra of pure water under the same conditions. But when this first principal component of the spectra of pure water is used to declutter the signal in an EMC procedure, then the first principal component of the salt solution for the different salts starts showing additional patterns, so an additional, more clearly some additional possible water coordinates. Still remaining into the domain of unsupervised or exploratory analysis or semi-supervised modeling, then one interesting method that is that has been used in a few publications, but also is not much used yet in the domain of aquaphotomics is the possibilities of using curve resolution methods. So curve resolution methods are actually, from a mathematical standpoint, they are bilinear methods just as principal component analysis. So if you think about the idea or the knowledge that you may have about principal component analysis, then thinking about MCR or multivariate curve resolution is thinking of another way of doing a similar decomposition of the data into a set of meaningful profiles that, for instance, can be used to describe the main phenomena occurring across the samples and maybe to extract loadings that can be used, for instance, to define water patterns or water absorption patterns, and then WMAX as well. Then, and of course, once you define this profile, you also define the relative contribution in the different sample of these profiles. So just like scores and loadings. But what is interesting about multivariate curve resolution or curve resolution techniques in general is that we are actually subjecting the data to different constraints from the mathematical standpoint. So we do the same decomposition, but then we aim at having something that is more closely resembling to standard Beer's law, so where we can interpret directly the scores as relative concentration and the loadings as actually spectral, normalized spectral intensity, or let's say extinction coefficient patterns, extinction profile for the different substances. So we look directly into the chemistry of the data. This is just to show that, of course, if one writes down Beer's law in matrix vector terms, one ends up exactly with the same equation as PCA. So matrix of concentration times matrix of spectral profiling transposed. But this is important because, of course, it gives us the opportunity of looking to our data with a lens of method that is similar in terms of how can we interpret it to a method that we already know. So we have a bilinear decomposition both in PCA and in MCR, and actually we end up with two matrices both in PCA and in MCR. But what is the difference? Is that, of course, the aims of the two methods are completely different. When I'm considering PCA, I want to explain as much as possible of the variability in my data. And of course, this is something that has some advantages because it's quite effective in summarizing the main source of variation within our data in a few latent or abstract variables, but it also is a disadvantage in the sense that, of course, if the source of variation is something that we do not want, then those will be the sources of variation that will be captured first. And this is why we have spent, or we are still spending so much time in speaking about how to get rid of all this spurious information, or how to rationalize the impact of temperatures, humidity, salt concentration, and all the different sources of variation in our data, because then we want to extract the underlying meaningful structure that we want, when probably this is only 1% or 0.05% of the total variability. We must be very honest with respect to one another in the sense that, of course, MCR, I will go very quickly, I will skip some slides and go very quickly about some specific, let's say, chemometric details about the algorithm, but MCR is still, in a way, a least squares method. It means that even if we not directly go to cover the direction of maximum variance, still it will try to give us relevant profiles that are relevant to describe the variability in our data. So we will not get as a first component something that explains 0.01 of total variance. Otherwise, we would be completely misled in our interpretation. But still, we can try to input as constraint information that is more chemically relevant than the one that we would have in PCA, because that is no chemical information is used in building the model. We use it for interpreting it, but we don't use it for building the model. And when it started, multivariate curve resolution was using as an informative source just non-negativity. Non-negativity for the greater majority of chemical and spectroscopic data, not for all, of course. If we think of circular dichroism, just to cite one, we cannot take into account. But non-negativity of spectral profiles and concentration, let's say, is the minimum chemical constraint that we can input in most of our data. In some other case, we can assess, put unimodality. For instance, if we think that we have just one peak for each of the single species that we want to investigate, but we can always, I will just skip this part, for instance, input mass balance if we are considering a transformation or a kinetics. So we can have also not only just mass balance, but whatever physicochemical model that we may think that our data may follow, we can input it as chemical constraint to the data. And then just the model is quite simple because, of course, one could think that we want any way to find components that have interpretative properties, so they are able to explain variance, but then they may be chemically relevant. Is resolution, but the greater advantage of this approach from our standpoint is that we don't need to do any guess, any informed guess about what the shape of the profiles that we are expecting should be. So in that case, in such, let's say for such characteristics, we can think about curve resolution as an unsupervised exploratory tool, in a sense. Of course, the more the information we have for our data, the more we will help the resolution. So if we know the profile of one of the pure constituent of our mixture, then of course if we input it, we may have better results. But it's not an obstacle in the case when we don't have such an information. And then of course the procedure is quite straightforward. In this case, we cannot rely on the same concept as in PCA, because we need to input constraint, and unless we do, and we may do it with quadratic programming on some fancy stuff, the best thing to do is something that is called alternating least squares, just a ping pong. So we just make an educated guess of one of the spectral profile, and we fit the concentration, and then we check whether this concentration shape would meet the constraint, the chemical constraint that we want, and in case we use this updated estimate to estimate the spectra back. And we do back and forth until convergence. So it's quite also easy in a way from its application standpoint. The idea, the general idea, and that's the most important probably concept that you may want to retain from this discussion about this part, is that whatever information we may code into a mathematical constraint, that would help the actual resolution of our data. And as an example, also here, I was taking a paper from by Rumiana and Ifa again, about the possibilities of using multivariate curve resolution on data collecting on solution of different solved with varying temperature. And in this case, data were analyzed with MCR that was showing 3 different spectral characteristics with profiles that were evolving, in this case, according to the shape that you see in the lower part, so in the score part, giving the idea of a process that with increasing temperature is proceeding, passing to an intermediate shape and then going to another structure. So with 3 structures that are in equilibrium, a different relative concentration was equilibrium concentration change in changing the temperature. So far from the unsupervised approaches. Then we have already heard about the possibilities of using our experimental data to make predictions. For instance, just in the example that was used before, to make predictions about a variation of a quantitative property. In this case, we are in the domain of what is called multivariate calibration. Then the general statement of multivariate calibration problems, especially for the simple case when there is a single property that we want to predict, is that we can express this predictive property as a function of the spectral intensities that we are measuring. And in the easiest possible configuration, when we assume linearity, so when we assume that a linear relation exists between the spectral and between the spectral shape and the property that we want to predict, then let's say that in a very extensively written form, the problem may be expressed in this way. So I have an offset, a general offset that I can get rid of if I do mean centering, but this is just technical. And then I may have a different linear combination of the different absorbances at a different wavelength, modulated by the coefficients that are here deemed as a B coefficient. And the idea, just to show it in a graphical way, is that I may approximate my y by the values that are corresponding to its projection on the plane spanned by the different coordinates that I am considering. Of course, taking into account that I will have a certain kind of error due to first of all, measurement error, but also it can be also due to model error or possible interference that are present in the data. And this is just the matrix way of stating the problem that may be used to describe the main characteristics of the models that we are normally used in this context. And the methods that are normally used to do this, especially in the domain of chemometrics, is the partial least squares approach, of which also you have seen mentioned also in the demonstration before, just a few minutes ago. So what is the concept within partial least squares? The idea between partial least squares is that we need to anyway give or try to use a parsimonious description of our data as predictors for the property or for the properties that we want to measure. This is because, of course, we have, let's say, technical problems. We cannot calculate regression models on a few objects when we have a lot of variables. But also, of course, because we would like ideally to have an idea of what are the meaningful sources of variation in our data, just as we do with PCA. Of course, we do PCA, we do dimensionality reduction or dimensionality compression because it's comfortable for us to deal with a few number of variables. But we do it also because we want these variables to be explicative, because we want to have an idea of what is the correlation structure that is underlying behind our data. So it's not only because, of course, it's normally when we introduce methods, it's yes. When we cannot use MLR because we have thousands of variables, we go to PCR, component regression, or PLS because then we can calculate the model. But it's not only because of this. It's because we want a meaningful representation of our data also in the domain of multivariate calibration. And just to give you an idea for the person that probably may not be familiar with partial least square regression, I will give first a very qualitative idea behind the algorithm, because the problem with PLS is that sometimes it's difficult to understand it without referring to the original algorithm. It's more an algorithmic method than a conceptual method, but we can also put the concept behind the algorithms and make it understandable. So what's the idea? The idea is that I want something that gives me the underlying structure of my data, both in the exploratory, in the predictive part, so in my predictors, in my spectra, and in the property or properties that I want to analyze. And in the general case, then I may want to predict more than one property given the same data set. So I will have multiple columns with responses. So the idea that behind the PLS algorithm is that I will try to summarize as much as possible the variation in Y using a component model. So let's think that I'm doing PCA, so that I am extracting scores and loadings to describe the variation in Y. And of course, I'm doing the same and using scores and loadings to describe the variation in X. Then these two sets of scores will individually have maximum variance in describing their respective matrices. But then I want something more. I want my X score, so I want my X block to be predictive with respect to the Y. So to describe the variance in Y, not only the variance in X. So if this is the direction of my first X score, and this is the direction of my Y score, then what I would try is just to do a slight tilting and move one in the direction of the other. That, put in mathematical terms, I will make a linear regression score by score. So I will try to make the score in the Y block linearly dependent from the scores in the X block. And this is what is called the inner relation. And sometimes this part of the PLS algorithm is forgotten, and it's a pity because this is the part also where if I'm not satisfied on a linear model, then I can decide to input a nonlinear one. For instance, instead of having a linear relationship between U and T, between the X scores and the Y score, or better, the Y scores and the X scores, then I could make it quadratic. And then I have a nonlinear regression. still within the framework of the general PLS model. So the thing is that what makes PLS a linear model is that particular inner relation, is not the overall part. Because then I have two linear projections for scores, but then what makes me a linear regression model is exactly this part here. Is the part also where I can act in the moment when I think that my prediction need not be linear anymore. Then when I'm summarizing all this concept, this is the concept that tells me, if I want to put it in an algorithmic way, or it's things that are normally used in books to describe PLS, that PLS search for a direction where there is maximum covariance between the X and the Y blocks, or better, between the X scores and the Y scores, in the case where I have multiple variables, because otherwise it's just between the X scores and the Y. And this is a graphical example of this concept. So here you have a data set, very stupid data set, but it's like two-dimensional data set where I want to predict a Y, a single property. And if I take just the first principal component to use the score of the first principal component to be predicted for the Y, this is the regression on the right side of the plot, you see that I have a very poor regression coefficient. So this is what I would do, for instance, in PCR, in principal component regression. Sometimes I'm let's say, lucky, because the direction of maximum variance is also correlated to the property that I want to predict. So it's not that PCR is not working. PCR works very well with many data. But sometimes the direction of maximum variance may not be the direction of maximum predictivity or maximum covariance with respect to the Y. This is the PLS first component. So you see that it's not that much tilted from the PCA scores, but still it has a tilt. So these loadings, this first principle latent vector in PLS is accounting from a good amount of variance in X, because it's still accounting from a relatively high amount of variance in X, but also it takes more into account the correlation with the Y. Now I see, if I plot the score and the Y, one as a function of the other, that with respect to the first principal component score, in this case, data are starting to be aligned according to this direction. And this is the general case, or the general scheme of PLS. Or now, for newcomers or for people that are not very familiar with PLS, and also for thinking about what can be of interest for this community, on which kind of loading or profile to use to construct or to build aquagrams on, or to define water coordinates from. So problem is that I think the most difficult things to understand in PLS is that with respect to PCA, especially with the algorithm that is normally used in most of the application, we have two sets of loadings. We have weights and we have loadings. And sometimes we have to decide which one to use for interpretation, because of course the ideal response would be both. Because we have different, it's like taking the same picture from two different angles. Problem is that PCA and PLS with respect to PCA has row spaces and column spaces that are different. So the row space is the space that is the space of X, and we model it by the loadings. The column space is the joint column space of X and Y, and we model it with the weights. So there is these difficulties because we need to have weights to calculate the scores, but then we need loadings to put the scores or deflate the scores onto only the X space. So when we are thinking about interpretation, then we have this duality and we have this problem. Of course, one way of summarizing the two is to take in this R coefficient. This is something that is normally automatically done when calculating PLS regression coefficient. So If you are not familiar with just thinking about this, think about what is normally done. Take PLS regression coefficient, because they are just scaled version of this regression weight. They are scaled by the value of the y, but this is just exactly the loadings that the set of, let's say, spectral profile that results from the superposition of the two. So far, for instance, this is the alternative that has been used when discussing the application of PLS in aquaphotomics to define the water patterns and the water coordinates. But sometimes maybe it could be of interest to try to look into the difference, for instance, into the individual loading weights or loading themselves to try to inspect the model parameters. Also because, and this has been reported by already, let's say, in the beginning of the 90s, and it's true for all kinds of regression methods, especially when they are calculating on data having possibly overlapping profiles. In the case of overlapping profile, regression coefficients, of course, do not match the pure spectra of the constituent, but they have to take into account all the orthogonalization with respect to the interfering phenomena. And you see it here with this, let's say, toy example, when we are interested in the blue analyte. And of course, even when we are over interference that are not interested but distant in the spectral wavelengths, then the regression coefficient is not, let's say, is not affected by the presence of the interference. But as soon as an additional band is overlapping with the band of interest, then we start to see awkward things in the shapes, and especially negative part, of course, and the regions of interest extends over the band of the analytes we are interested in. So we should be very careful every time that we use regression coefficient, or for the same reason the R weight, to interpret the PLS model, because this could in some cases lead to misleading interpretation. Of course, when we are in the domain of regression, we have many ways of enhancing interpretation that are, some are specific for PLS approach, an informative variable elimination or selectivity ratio, VIP score. Some are more general, independently of the specific tool. So if you use PCR, if you use MLR, if you use support vector regression, then they may be generalized as well. And of course, additional tools may come from the idea of using some variable selection to identify spectral regions or specific bands that may be related to the phenomenon of interest. It must be very honestly said that variable selection techniques are mostly sold as a way of improving predictions, but in reality, and if proper validation is made, and if you consider confidence intervals of prediction, normally it's quite rare that you improve prediction of models. But the truth is that you may improve interpretation of models. And in this we have the advantage that we have a lot of models and methods that we can use for variable selection in the domain of regression and classification. And here you may see that normally, especially in the recent literature, they are trying to be classified according to their main characteristics. So something that use model parameters a posteriori as a filter, for instance, use of VIP scores, use of selectivity ratio, and so on. Some that works on extracting or repeatedly extracting subset of the original variables, for instance, like genetic algorithms and or interval-based methods, and so on. And also, there are the possibilities of using, in general, sparse methods when the variable selection is directly incorporated into the method itself. So this is just some general comments, I would say, about the characteristics, especially of the filters and on the embedded methods. The idea is that, in general, filter methods, it's something that we do also when we consider regression coefficients and try to base our interpretation and our identification of bands on those values of coefficient, loadings, and whatever. Because the idea is that we just calculate our model and we use model parameters as a mirror to try, or let's say as a filter in real sense, to try to define which variables that contribute to the model may be relevant to the definition of the model itself. The advantage is that they are fast, because you compute the model, you already have it for free. The disadvantage is that, of course, quite often you have to decide, because you will have a value of, let's say, importance indices for the different variable given the model, and then you have to decide where to place a threshold. And doing this is often not trivial, or at least it may be trivial, but it's not often guaranteed that it gives you relevant results, especially if interpretation is the task. And okay, it may not be the case directly for the aquaphotomics application, but also it's not guaranteed that the subset, you have no information at that stage that the subset of variables, let's say the bands that you isolate, may also have a real predictive improvement or predictive ability per se. So this is another different advantage. Well, with the wrapper methods, let's say, is something that you may associate often with evolutionary calculation. So you do some extensive subsampling of your data, and then you try to compare the submodels and that you have extracted. It may be in a consensus way, it may be in a winner best takes all way, but the idea is that you still are considering directly models built on subset of variables in defining or in checking the goodness of the performances of the variable selection method one is performing. So you may get extensive subset search that can be randomized or deterministics, and these are examples of different methods. And the deterministics have the disadvantage that the exploration is quite unfavored with respect to the exploitation properties. So you may not try a solution that in principle could see, let's say, less likely to be tried, but of course they have the advantages of being quite fast. Some few words, just a few, on the possibilities of predicting qualitative variables. So sometimes we want to check, or we want to correlate the experimental results to a variable that is qualitative in nature. So it's not quantitative, but it is qualitative, it is discrete. And let's say the prediction of discrete variables is what we normally would call classification, because the different levels of the variable that we want to predict may also be called classes. An example was in one of the workshops of the afternoon, when the idea could be, for instance, to differentiate the nature of the different solutes that are present in the water samples that are collected. And in this respect, we have different approaches that we can use for classification. There's the so-called discriminant approach, or discriminant classification, where the idea is that in my training set, in the data set that I'm used to build the chemometric model, I have a certain number of the different classes that are represented. And I decide that these classes cover extensively the range of classes that constitute my problem. It means that, for instance, in this case, I colored them in different color. I have 3 classes, and the 3 classes are the red, the green, and the blue. And discriminant classification model look at those data and use the information about the class of the different samples, of the nature of the different samples, to build boundaries. And these boundaries have the characteristics of being open. It means that they cover exhaustively the whole data space. It means that when I have a new sample, and I will try to place it, of course I will measure, in this case, a spectrum, and I will place it in one particular region of space, then it will be predicted as being only A, B, or C. So I will just have an exhaustive winner-takes-all classification. So I have 3 classes in my training set. Each prediction that I will make would be either A, B, or C. Of course, this is quite limiting under some respect. There's also the advantage that in some cases, in most of the cases, of course, I need less sample, and discriminant approaches are more effective when classes are underrepresented. So that's the reason why they are normally being the most commonly used in the literature. But one can think of a different way of doing classification. That's the one that is generally called as modeling classification or class modeling in general. And the idea is that I may think of all the objects that constitute a class, so all the objects that represent a particular condition, to be those that give me information on what makes each sample within this class similar to one another. So let's think, if you want to think of an example in this case in the domain of aquaphotomics, you may think that I have a set of samples with different kind of solutes, and then I have pure water. And pure water then can be, for instance, my class that I want to model irrespectively of what is non-pure water, because then the non-pure water class can be quite heterogeneous depending on the design that I've made. And then I can decide to model only the variation of a class that I can homogeneously sample and represent. In those cases, that would mean to have only the samples from class A. And class modeling would build a boundary around these class A samples and define only what is A and what is very likely to be not A in this context. Of course, this doesn't mean that if I have a second class that is still, let's say, homogeneous enough or defined and well represented in my training set enough to be the base for an additional model, to build the second model completely independent from the first, from that particular class. And this second model can be anywhere in space depending on where my samples are. For instance, if the second class be class B, then I would have a class space, a class boundary that would be partly overlapping with the model of class A. But if it be class C, then I would have a completely isolated class space on another set of the plot. And what's the advantage of such an approach is that whenever I have a new sample, it will fall on some part of the space. And then it may fall in the regions of space where I have only class A, for instance here, yes, you see it. It can fall on the region of space when I have only class B, but it can fall here. And here I have the additional information that that particular sample may either be A or B. So it's in a position where, like, my decision could be blurry, or anyway, it could have a high enough degree of likelihood to be from one part and from the other. And more interestingly, if I have a sample that falls in this part here where no training sample was mapped and no class space is defined, then I have information that that particular sample may be something else, maybe a measurement outlier, maybe something different, maybe even a fourth class that was not representing in the training set. So I have a richer information, but of course I pay it at the price that each category should be representative enough to be a meaningful model of its class space. Otherwise, of course, if I have loosely representative classes, then my class space could be large enough or short enough not to include real samples belonging to that class, or large enough to include whatever sample from the other categories. I'm almost finished. I will skip the details about specific methods for classification because I want to spend the last 2 minutes to speak about an important concept that is and should never be forgotten. That's the concept of validation. So the idea is that whenever we build a chemometric model, of course with different tools depending on whether we are doing exploratory analysis, we are doing resolution, or whether we are doing truly predictive modeling, whatever the kind of approach that we are following, we still be able to, or we still should properly validate our conclusions. And as I started saying in the beginning, validation should cover everything, not only the results of the data. It should cover validation of hypotheses, validation of subspaces, validation of interpretation or extracting relevant variables, and validation, of course, of prediction when prediction are involved. And in general, then what we need in validation is defining, first of all, a proper diagnostic. So something, a number, a series of numbers, figures of merits that tells us that something has gone wrong with our data or that something is good with our data. And the good thing is that since models that we built are approximations, then we may think that residuals, that means difference between our approximation and the data that we have, can be the suitable diagnostics for judging how good the model is in the validation phase. Because residuals have many properties that you may see there, and they may be important in helping us assessing which models to use. In components-based methods, they may be helping us to define which is the optimal complexity of the model to use. Of course, since they are residuals, they may give us information about predictive abilities, but also, since we may have different entities in residuals depending on the situation, they may give us a hint about the possibilities of overfitting the data. And additionally, we may do a residual analysis to check for additional structure if we may suspect phenomena that we're not taking into consideration when we are doing our modeling phase. However, when we speak about residuals, so once we identify the diagnostics, we also need an additional step. Because due to the least squares property of most of the methods that we are using in our common chemometric analysis, if we would use only the residuals from modeling, so from the data we used to build our model from, then we will still not have a reliable information. Because both the entity, so the dimension, and the structure of the residual that we have from our modeling set will never, or let's say almost never in practice, resemble the structure and the entity of the residual that we may be expecting when we are analyzing new data. And this is something that is inherent in the kind of models that we build. So it's like Snow White's mirror, or Snow White's witch mirror. It will give us the answer that we want, the over-optimistic answer that we want. So, of course, what's the tools that we want? We want to estimate our models on new data. New data, of course, for which we, in case of predictive modeling, we know the answers, because otherwise we cannot calculate any kind of residuals. And the ideal case, this is always the ideal case, and that would be the last take-home message, would be to have a new independent set of data that is collected in as closely as possible the conditions, experimental conditions, that you are expecting from the new measurements. And that would be the optimal case. Of course, sometimes we can rely on resampling, such cross-validation, bootstrapping, jackknifing, and so on. But of course, having a new set of data, completely independent and as close as possible as the condition of sampling condition that you would expect for new data would be the optimal way. So, thank you, and if you have questions, I will be here, of course, not only now, but also for the rest of the symposium, and I will be happy to take whatever question you will need. Thank you.
For that discussion. Any question, comment? I have a question.
Yes.
About the MCR.
Yes.
How do you estimate the number of components
Okay.
in case of temperature dependence?
Yes. So the number of components of temperature dependence was not my study. So, but I can tell you that they were trying 3 and 4 components specifically and checking the interpretation of the results. So, let's say that when you are considering MCR, you have tools to estimate the number of components. The first thing is that the space that is spanned by the MCR component is the same space that is spanned by PCA. So the true chemical rank of the matrix is the same. So it means that at first, of course, with all the problems associated, so it should be taken with the appropriate care. Doing a PCA or an SVD of the data matrix would give you an idea of what could be the optimal number of components. But of course, in some cases, we know that script routes, script routes of the PCA, cross-validation and whatever, may not give a proper estimate of the true number of components in the data set. So the additional advantage of MCR in this context is that normally you would try to fit, let's say that you've seen that your optimal number of components should be 5. So normally what you would do, you would try, let's say, from 3 to 7 components, and then also look at the stability of the spectral profiles, because you would likely see profiles like in PLS when you add too much components. You would see profiles that get noisy if you go over the proper number of components, but also since MCR is not sequential, differently than P. So model with 4 components is not model with 3+1. Then you will have to look at global interpretation. But you have the tool of having chemically meaningful profiles. So you can check whether interpretation may be consistent.
Because we can sometimes find, for instance, the 2 components, 3 components, the interpretation is completely different.
It is. Well, especially when you are not estimating all of the, between 2 and 3, of course, it may happen that with 2 you don't have enough degrees of freedom to estimate the meaningful variation in the data. But sometimes, of course, let's say that with 2 you estimate you explain 85–90% of variance, and with 3 you explain 97. But sometimes the problem is that with 3, 4, and 5 you explain 98.5, 98.9, and 98.99. And in some cases, then also spectral profiles are almost all reliable, and then it's difficult to decide. I agree.
So, do you have any question, comment? Okay, thanks again.
Thank you.
So today's workshop is called